Alright, so we're looking at vectors and matrices, and we have three vectors and the components given, 3 and 4 for vector OP, negative 1 and 2 for vector PQ, and 1 and 3 for vector RS. And we're asked to determine the vector OQ. Now for us to go from O to Q, alright, looking at the vectors that we have from O to P, but that's it. But if you notice that we have from O to P and then from P to Q, so we could use these two vectors to determine vector OQ. So we want a transition point. In other words, we're going to go from O to P and then from P to Q. So OP plus OQ in terms of vectors will give us OQ. So the concept is this: if I want to get from O to Q, so let's say we have this triangle. So let's say this is O and this is Q. Here we have P. Alright, so instead of going from O to Q, we can go from O to P first. Alright, so this will be vector OP, and then from P to Q. So OP plus OQ is the same thing as going straight from O to Q. Alright, but we don't have the components for OQ, so we're going to try to derive that. And OP, we got the components 3 and 4, and there should be PQ, right? So from O to P plus P to Q. Alright, O to P, P to Q. And P to Q is, PQ, vector PQ is negative 1, 2. When we add these, we're going to have 3 plus negative 1, that's 2. So we're going to add corresponding components, which are the x components. And then we're going to add the y components, 4 plus 2. This is the operation here, which gives us 6. And so we can say vector OQ, which is the sum of vector OP and vector PQ, is equal to 2, 6 in terms of the components. Alright, so that's the first one. So we have completed the first one. And the second part asks us to do what? It says to show that the vector OQ is parallel to RS, given a reason for your answer. Alright, so there is some vector RS that is parallel to OQ. And the thing is about parallel vectors that are parallel, it means one is a scalar multiple of the other. So we have to just prove that one of these vectors is a scalar multiple of the other. So let's look at what RS is. We're given RS as the column vector with components 1 and 3. So let's write that down. So we're given that RS has components 1 and 3. Alright, can we show that one is a scalar multiple of the other? If we look at the components for both vectors, we can see that if we were to factor out 2 from 2 and 6, factor out 2, we'll actually end up with this. Let's look at it. So let's put factor out 2. 2 times 1 is 2, and 2 times 3 is 6. Because remember, you're multiplying a scalar by a vector or even a matrix. You multiply the scalar by each component. So 2 times 1 give us 2, and 2 times 3 will give us the 6. So this is still, in the sense, vector OQ. We just factor out the 2. That's vector OQ. Alright? Same as this. But we do recognize that this is actually vector what? RS. So we can say vector OQ is twice the size of, or twice the length of vector RS. Alright, so that's the idea. Now once we have shown that one vector is a scalar multiple of another, then both vectors are considered to be parallel. So we can say therefore vector OQ is parallel to vector RS. Alright, and then you can put in the notes, since vector OQ is twice the length of RS. Alright, and it's a scalar multiple of it as well. So you can put those notes, and that's it. Alright, but now let's look at the next part of the question. So part B, it says here, triangle XYZ is a or should I say XYZ is a triangle, and M is the midpoint of our XZ. XY, or vector XY is equal to A, and vector YZ is equal to B. And then we are to express these vectors in terms of A and B, simplifying our answer where possible. Alright, so basically we want to, it's nice if we could just construct this triangle first off as a sketch, so we can actually have an idea what we're doing. And so it says X, Y, Z is a triangle where M is the midpoint of YZ. So we're going to go, where's YZ? Or XZ. So XZ is here. So we can put M there. Right? Okay, so M is the midpoint of XZ, as we're told here. In the middle of it, in other words, the point there. So these are the 3 points, X, Y, and Z, the vertices of the triangle. And now they're saying that XY, vector XY, so if we're going from X to Y, vector XY is A. So we can put the small a here, indicating from here to here is the vector A, and which is same as saying vector XY. Vector YZ, going from Y to Z, right, remember this is vector XY, is B. So we can put B here, or we can just put it here as well. So they're basically the same things, right? We just wrote the vectors in terms of A and B. So vector XY written in terms of A, vector YZ written in terms of B. Now they want us to write vector XZ, going from X to Z, in terms of A and B. Alright, but what we know based on the triangular law of vectors, if we want to get from X to Z, so let's write that. Going from X to Z, we can go instead from what? X to Y, and then Y to Z. So vector XY added to vector YZ. Okay, so going from X to Z, we can go for XY, that's vector XY, and vector XZ. XZ, yes. Now vector XY is really A, and vector YZ is really what? B. We're told that, right? Vector XY is A, and vector YZ is B. And so we have written vector XZ in terms of A and B. Very simple. And the next one is vector MY. It's right here. Right? So we're looking at MY. So that's second part. Okay. We want vector MY. In other words, we want to go from the point M to the point Y. So, alright. Probably should not put the M there. But we're going from this point, which is representing M, going to this point. How do we go from M to Y? Well, we can say we're going from M to X, right? And then from X to Y. We know the vector here, right? The vector from here to here, right? Which is parallel to this, which is same as this in essence, is going to be what? Vector A plus B, right? Two vectors that are parallel and the same length carry the same vector. So we're saying from here to here, which this is A plus B. So if we want to go from here to here, it will be what? Half of this, isn't that so? So we're going to go from M to X, and then from X to Y. And at the end of it, we'll have gone from M to Y. So start from M, go to X, and then from X to Y. So vector mx plus vector xy will give us the same vector as vector my. So technically this is what we're having, guys. Alright, this is m, this is y, and this is x. Alright, since this is this is vector A plus B, then from here to here will be half of it, half of A plus B. Alright? Think of this as 10 meters. From here to here will be 5 meters, right? If this is the midpoint. So it'll be half of it. So whatever value this is, from here to here will be half of it. Now from here to here is A plus B, then from here to here will be half of A plus B. Okay, so we're going from M to X, which is half of A plus B, and then going from X to Y, we already have that as A. Alright, so MX is half of the vector A plus B added to vector XY, which is A. We can simplify that. Simply half times A will be half A, half times B will be half B plus A. Now they did tell us to simplify answers where possible, and since we can simplify this, we're going to do that, right? And this is easy, guys. Think of this. This is half A, this is 1A. So we're adding 1 to half. Now if you can put this in your calculator simply, right? Just put, dependent calculator you have, by the way. You could, well, 1 plus a half is 1.5, right? Simple stuff, right? 1, so you could just put it in your calculator. I mean, you might not get something that simple, right? So what I did here, I press 1, then this button. Probably cannot see it. I press 1, then this button here, and it automatically gives me the 1 on top, and I'll just put the 2 in. Press equal. Notice that it actually gives me this, right? So 1 plus a half is 3 over 2. All right. But that's something that you know you should be able to work out. But in case, that's fine. 1 plus a half, that's 3 over 2. Because 1 plus a half is really 1.5, right? 2 ones, 2 plus 1 is 3 over 2. All right. So when we add the a's together, we're gonna get 3 halves. In other words, because 1 half can be written as 2 halves, isn't it? Well, that's just 1 half. 1 can be written as 2 halves. Think about it. If you have something, you have a whole, you can divide it into 2 equal halves. And 2 halves plus 1 half will be 3 halves. That's another way of looking at it. Plus a half b. Alright, so what we're going to do next? Well, what we can do next, we can take out a half, right? It's like a lot of work, right? We can take out a half from this if we want. I mean, I think this should be fine, right? But we could take out a half, and in the end we should have, if we take out a half from this, then we're going to have the 3, right, which is on top as 3a there, and since we pull out this half, it will be just b, and that will be our solution. All right, but it's perhaps they will give you this, but I guess because you can factor it out, that's one way of looking at it. But I will say this is fine as the solution in terms of simplifying. So we cannot add these two quantities, but write it in another form is something else. Okay, so now that you understand that, let's look at the next part. Well, part C. Alright, so we have two matrices, A and B, and where A is a 2 by 2 matrix, right? 2 rows and 2 columns. And then we have matrix B, which is a 3 by 2 matrix. We have 3 rows, 1, 2 columns. And they're asking us, basically what I just did there refers to the order, right? 2 rows, 2 columns is a 2 by 2. And 3 rows and 2 columns indicates a 3 by 2 matrix. So we call those the order of the matrix. 6, you could well ask a question on that. Perhaps we will see. Now determine the inverse. This means the inverse. The negative one here, when we're dealing with matrices, mean the inverse of matrix A. As it says here, the inverse of matrix A. Alright, A is a matrix. Matrices A and B. So when we see A, we just refer to it as matrix A. Alright, so to find the inverse of a matrix, what do you do? Well, to find the inverse of a matrix, we want to find the determinant of that matrix. So we're going to find the determinant of matrix A. Right? And this is this for short. What we do, we multiply these guys, these elements. We call this the leading diagonal. Right? Think about a square. This would be one diagonal, and this would be another diagonal. So, our rectangle. So one that they call it leading diagonal, non-leading diagonal. So multiply these entries, -2, -1 times 2. Alright, so we multiply -1 by 2, and that gives us -2. Alright, I was going to put the product inside of say -1 times -2, but I changed my mind, hence this the bracket here. So we can probably erase that bracket. Alright, I'm just going to work the answers out. So -1 times 2 is -2, minus 0 times 3, that's 0, and so -2 minus 0 is just still -2. When you add or subtract 0 from a quantity, it's still that same quantity. So the determinant is -2. How I got the determinant? I multiply these two and get -2, and then we multiply these as well and get 0, and we subtract both products. So that's the determinant. Now there's something else for us to find the inverse that we have to find, which is called the adjoint. So the adjoint of matrix A is found by doing this, by switching these guys in the leading diagonal. So I'm going to switch -1 and 2. Then I'm going to change the sign on these two numbers. Now since 0 doesn't have a sign, we just leave it at 0. But we'll definitely change the 3 to a -3. What we're really doing here is multiply these two quantities by -1. But -1 times 0 is still 0, and -1 by 3 is -3. Alright, so we switch these and change the signs of these. Okay, and I'm saying that in case you have a different matrix in your exam. Okay, now the inverse now is a combination of the determinant and the adjoint. So the inverse of A, which is written as A inverse, is equal to, alright, so you can write this, or if you want to write this alone, it's fine, is equal to 1 divided by the determinant of A. So let me just write that. 1 divided by the determinant of A multiplied by the adjoint of A. Okay, so that's the formula. So write it as 1 over -2, because -2 is the determinant that we found, multiplied by the adjoint matrix. 2, 0, -3, and -1. Alright, it's good practice sometimes. Well, it's good practice to just simply to multiply this out. Alright, so -1/2. Now when we have a negative in the denominator or the numerator, we can put it at the side, right? So let me just write, well, we don't have any space here, but this is really the same thing as saying -1/2 or -1/2, and then we have the 2, 0, -3, -1 there. So we can put the negative at the side. Once it's here or there, we can put it at the side. Same meaning. So now negative, we're going to multiply each quantity inside a bracket by the -1/2. In your calculator, considering that 1/2 is really 0.5, you can say -0.5 times 2 and get your answer, right? If you're not if you're struggling with multiplying these out, okay? But half of 2 is really 1, and negative times positive is negative, so that's -1. A half of 0 is still 0, right? Any quantity multiplied by 0 is 0, so -1/2 times 0 is going to be 0. A negative times negative is a positive, right? Because it's -3, and then we're going to divide 3 by the denominator of 2. Alright, so really you've taken these these integers and divide it by the denominator, since we have a 1 here. So 2 divided by 2 is 1, that's -1. 0 divided by 2, still 0. 3 divided by 2 is 3/2. Of course, you have to consider the signs already, right, as well. Negative and negative is positive. This is 1 divided by 2, which is a half. Remember, negative times negative make it positive, right? So that's what we have for the inverse. They may accept this, but it's good to complete it like that as well too. Now here's what they're saying here afterwards. They're saying to show that A inverse, there's a -1 here, A inverse times A is the identity matrix. So let's look at that. Alright, so recall what we have for matrix, for the inverse of A, right? It was so A inverse times A equals the identity matrix. We can do it two ways. We can write it as 1 over the determinant times the adjoint times matrix A, showing that we'll get the identity matrix. Or we can use the, go back to this. So I was saying we can either use this, which is A inverse itself times matrix A itself, and then, or we can use this. All right, let us use this one. All right, so A inverse, which is we'll put the A inverse first, which is -1, 0, 3/2, and 1/2. That's an A inverse. And we're going to multiply it now by matrix A, which we were told is -1, 0, 3, 2, right? 2 by 2 matrix with these components. Now when we're multiplying two matrices, all right, we multiply row by column. Now remember what they told us, that when we multiply these we should get I. Now I is the identity matrix, which is the 2 by 2 matrix with the leading diagonals being 1, right? The elements in the leading diagonal, are 1, right? And the elements in the non-leading diagonal are 0s. All right, so we multiply row by column. This is what we're going to get. So we're going to say row by column. So we're going to go -1 times -1, that's +1, plus 0 times 3 is 0. So we multiply row by column. First times first, that's +1, plus the second by the second, 0 times 3 is 0. All right, so that's row 1 multiplied by column 1. Take these guys out for now. This is row 2, this is column 2. So rows of the first matrix by columns of the second. So row 1 times column 1 goes into row 1, column 1. Row 1 again times column 2 goes in row 1. So we're still in row 1 since we multiply by row 1, but by column 2 now. So we're over here. So -1 times 0 is 0, plus, so first by first added to second by second. And 0 times 2 is 0. We don't have any more columns, so we go down to the second row. So our answer will be in the second row, since we're multiplying by the second row. 3/2 times -1 is -3/2. Remember, we're multiplying -1 by a number. So the only thing that will change is the sign, because 1 times any quantity is that quantity, and negative times positive is negative. So we multiply the first by first, gives us this, plus the second by second. 3 times 1/2 is 3/2. Okay, remember, we're going to take the integer and divide by the denominator, since the numerator is 1. So 3 divided by 2, that's the solution there. Okay, here you just use your calculator, as a matter of fact, too. Now row by column. 3/2 times 0 is 0, and half of 2, half times 2, or half of 2 is 1. Let's simplify this. This will give us 1, this will give us 0, this will give us 1, and notice that these are the same quantities except the signs are different. In that case, you get 0. Different signs of the same quantity, you subtract. Or different signs with numbers, right? You're gonna subtract, and you're gonna get 0 in this case. So that's the solution. And of course, this is the identity matrix. All right. And so we have basically shown that QED. All right, means that we have shown or proven. We have proved the point. Okay, that when you multiply a matrix by its inverse, or inverse of a matrix by the matrix itself, you get the identity matrix. All right. So the next one is finding A squared. Okay, so A squared, let's find that. We have A, which we know is this matrix here. And by the way, you might be wondering, why am I using curved brackets if they give us some squared brackets? No, it doesn't matter if you have curved or it's being squared. Alright, what I'm saying here, they could either do this or have them written like that. Alright, so it doesn't matter if they use these type or these type. Alright, it would fine. Now what we want to find is A squared. Now what it means really, when I say A squared, that means that you're multiplying the matrix by itself. Alright, so you mean matrix A multiplied by matrix A. And so you don't want to go and do something else, but you have to do this, right? So what you're going to do is going to take matrix A and multiply it by itself. So you have to go through that process. Don't square these numbers. It's simply saying matrix A times itself. Just like you have 3 squared, which means 3 times 3, but it's matrix A times matrix A. But the process is different because when you're multiplying two matrices, you multiply row of the first by column of the second. So we have to go through that lengthy process. Alright, so now we're going to multiply row of the first matrix by column of the second matrix. Now, row times column, -1 times -1, that's +1, plus, of course, row 1, row 2, column 1, column 2. So it's first times first added to second times second, and 0 times 3 is 0. That's row 1 by column 1 goes here. Now row 1 times column 2 will be over here in row 1 still, because we're multiplying by row 1, so we stay in row 1. We're staying in the right lane. -1 times 0 is 0, first times first, second by second, 0 times 2 is 0. Now we go down to row 2, row 2. 3 times -1 is -3, plus 2 3s, 6. So that's row 2 times column 1. I'm saying row 2, column 1. Row 2 times column 2 will be over here, row 2, column 2, right here. 3 times 0 is 0, plus 2 2s, 4. And so our solution will be 1, 0, 4. And -3 plus 6, signs are different, we subtract, keep the sign of the bigger number, right? And what's the bigger number? We're talking about the bigger number that's in terms of the absolute value. We ignore the signs and say which number is bigger. Well, the 6, and we keep that sign. Alright? But of course their signs are different, that's why we subtract it. Alright? Or just punch this thing in your calculator for paper 2 and you're good to go. So that is what A squared is. Alright, let's look at the final part of this question. Alright, so for the final part, they say here, explain why the matrix AB is not possible. Alright, so why matrix AB is not possible? In other words, multiply matrix A by matrix B. So let's look again and see what these two matrices are. Alright, better yet, let's just go over here. So what we're seeing here, as a matter of fact, is that matrix A, in terms of the order, we have 2 rows and 2 columns. So it's a 2 by 2 matrix. Matrix B, on the other hand, has 1, 2, 3 rows and 2 columns. So it's a 3 in terms of the rows by 2 in terms of the columns. If these two inner numbers are not the same, it's not possible to multiply the matrices. And since this is matrix A, the order being 2 by 2, this is matrix B, the order being 3 by 3, it's not possible to multiply matrix A by matrix B. Right? Right? It's not possible. And we can see why. Let's check it out. If we were to multiply a row by column, what will happen? Row by column. It will be -1 times -3 plus 0 times 1. But notice what happened? This number here would not be multiplied by a number in this row because we don't have a third number. So the row by column would not work for this. Row by, because we only have 2 elements in the row while we have 3 elements or components in the column. So when we multiply matching components in terms of first by first, second by second, we don't have a third. So we can see why that wouldn't work. Alright, so what we can say here in terms of what they want us to explain, we can simply say this, that the number of columns, right? Number of columns, so remember what we said earlier. Just get back this. This is matrix, the was matrix A, this was matrix B, right? This is row by column, row by column, right? These two guys must match. So we can say the number of elements in the column of A should be the same as the number of elements in the row. Right? Let me go over that again. I think I made a mistake here. Let me explain that again. The number of columns of the first matrix, which is matrix A, must be the same as the number of rows of matrix B. Alright? And since they're not, then it's not possible to multiply them. So that's what you basically state. The number of columns in A is not the same as the number of rows in should say that in matrix A in B. Alright? Hence A times B is not possible. They must be the same. Simple. You can add that as well. Okay? So the matrix A is a 2 by 2. Matrix B is a 3 by 2. Row by column, row by column. These guys should be the same. So the number of row by column, the number of columns, right, in this case for A must be the same as the number of rows for B, and we can see that they're not the same. And in terms of the resultant matrix will be these guys multiplied, right? Whatever number this is by whatever number that is, that'll be the resultant matrix. And the second part will deal with that, right? It says without calculating, state the order of the matrix product BA. Alright, for the matrix product BA. So B is, we're going to multiply B by A. So we don't multiply, by the way, but just saying. We have matrix B, and its order is a 3 by 2. We have matrix A, its order is a 2 by 2. And we can multiply B by A in this case. Why? Because we have the same number of, let's see, row by column, right? The same number of columns of the first matrix is the same as the number of rows of the second matrix. These two inner numbers must be the same. 2, 2, they're the same. And the resultant matrix will be the R times the C, the outer numbers. And the outer numbers, what do we have? A 3 by 2. So that would be our answer. The resultant matrix will be a 3 by 2. So in terms of our answer here, we'll put a 3 by 2. Alright, the order of the matrix product BA is a 3 by 2. Alright, so you just write it in. Alright, so that's what we'll put for that. There's the answer. Okay, so I know this video is quite long and this would have been the end of the video, but what if they'd given us a simultaneous equation? How would we have worked that out? Alright, a simultaneous equation. Let's see if we could actually add something else to this, where we have a simultaneous equation that we want to solve. Okay, so let's suppose they're giving us this simultaneous equation, negative x I think I'm going to change this. So let's put 2x plus 3y equals some number. Then we have x plus y equals some number. Alright, so let's say I'm going to make this up. X is 1 and y is 2. So it'll be 2 times 1, which is 2. And 3 2s is 6. So that's 8. Alright? 2 plus 6. Okay. And that will be 3. Okay, so this should be the solution that we get in the end. Okay, so we know x is 1 and y is 2, but we're going to solve and prove that's the case for this simultaneous equation using matrices. Okay, so the first thing we want to do, let's say they tell us to write this in the form of a b equals, not a b, let's use this instead, ax equal b. Like write as a matrix equation, alright, in the form of a matrix right, ax equal b, then our a matrix will be the coefficients 3, 2, 3. Pull the 1 from here, right? Because there's a 1 in front of x that we don't usually write, a 1 in front of y we don't usually write, and we take the variables x and y, put the x on top, y below, and the 8 and 3, the constants, we put them here. And what we do next after that? Well, what we're going to do is to find the inverse of this matrix, the coefficient matrix, and multiply by this guy. That's all we do. So the inverse of this matrix, remember we said the inverse of a matrix is written as what? 1 over the determinant. So we find the determinant for this first off. So it's going to be 1 over the determinant, which is 2 times 1, which is 2, minus 3 times 1, which is going to be 3. Alright, so it's 2 minus 3. Alright, so that's the determinant, 1 divided by the determinant, times the adjoint. So we're going to switch these guys. 1 goes here, 2 goes there. Change the sign on that, negative 3. Change the sign of that, negative 1. Alright, and then we're going to, so this is going to be the inverse, and then we're going to multiply it by this guy here. So we find the inverse of the coefficient matrix, which is what we have here. We still have to simplify it, and then multiply by this guy here. Alright, and that will give us x, the matrix with component x and y. So let's simplify that. 2 minus 3 is actually negative 1. So if we were to simplify that, 1, and we have 2 minus 3, that will give us 1 over negative 1, which of course is negative 1. So this will give us negative 1 times 1, negative 3, negative 1, 2, then 8, and well, we may choose 8 and 3 as components. We can do this two ways. We can work out this first of all, everything here, and then multiply by the whatever we have here, which is the safest way to go. Let's suppose this was a fraction, like 3 over 4 or something. Would have been best to just work out these two guys first, and the answer you get multiplied by this. So we can actually do it that way, just in case you get some fraction. Alright, so let's put back this, and let's multiply row by column. So 1 times 8, alright, we're going to multiply row by column. So 1 times 8 is 8 plus, so it's first by first, added to second by second. Negative 3 times 3, that's negative 9. Then we're going to go down here, since we don't have any more columns, so we have to go to the next row. Negative 1 times 8, that's negative 8 plus, we always add. Then 2 times 3 will give us 6, right? Yeah. And so now we have negative 1. 8 plus negative 9. Signs are different, so we subtract and get negative 1. Keep the sign of the 9. So 9 is more than 8 if you ignore the sign. Alright, so different sign, we subtract, get 1, keep sign. Different sign again with the numbers we're adding, so we're going to subtract, get 2. And we're going to keep the sign of the 8 since 8 is more than 6 when we ignore the sign. But we're going to keep the sign of the 8 because 8 is bigger than 6 when we ignore the sign. And then we're going to apply we're going to multiply these two elements outside by the number outside, right? In this case, we don't have a fraction, we have negative 1 instead, but we do the same thing though, right? Negative 1 times negative 1, that's positive 1. Negative 1 times negative 2 is positive 2. Negative change signs, right, when you multiply. Now, since these two are equal, call that equal matrices, then we equate our solution. X equal 1, y equal 2. Alright, we equate elements. And so we got the two values, alright, as we would have started with. So just remember, once you have a matrix, you divide it, we separate it into and they ask you to write it as in this form. You write the coefficient matrix first, you write the variable matrix after, and the constant matrix following. And you just want to remember that you want to make sure it's in this form, right? And the next thing, in case you have a minus sign here, what would you do? If you have a minus 3y, for instance, what will happen here? Well, in case you have a minus here, you treat it as a negative 3. Okay? You have negative 3 here. Because if this is plus 3y. So if they gave you minus 3y, you have to show that difference by using a negative instead. Because the thing is, I'm just trying to show you something here, because they could give you something like that. Let's say you had, let's say that a minus 3y, in case they're giving you that. Then you can rewrite this as what? You can rewrite this as 2x plus negative 3y equals 8. Same thing. So you end up having a plus here, right? But notice that what the coefficient of y is? Negative 3. Right, because this and this is the same. So just telling you that using a minus, you can always change it to a plus and change the sign. So you have plus negative 3y. So this would have been a negative 3 here, if that was the case. Okay, so that's it. Hope this review on matrices was helpful.